Yeah, good. So today I want to talk about the oscillations. So there's different type of oscillations in our world, and they're very common phenomenon. And last time I introduced ordinary differential equations, and these oscillations can be modeled by ordinary differential equations easily. So you can call this class an applied maths or a maths physics class. And this is my second lesson. So this is my table of contents. First, we will introduce three types of oscillations. The first one is just a simple harmonic motion. That is the simplest oscillation. The second one is damped oscillation. And the third one is forced oscillation. So let's see the simple harmonic motion first. This is the most simple one. And so to begin with, we have the definition of the simple harmonic motion. So we simplify it as SHM. The definitions like below. So the simple harmonic motion is the linear motion. The first one is it is a linear motion, and its acceleration, the acceleration of the object that is doing the simple harmonic motion is uh, proportional to the displacement, and is in the opposite direction with the displacement from an equilibrium point. So let's make some equation words, mathematical words. So the vector A, you can see the acceleration is proportional to the displacement x vector, and the the factor is minus k. So k is greater than 0 and minus k is negative. So it shows that the acceleration and the displacement are in the different direction, opposite direction. So there is some examples. The oscillation of a spring. So when a spring is oscillating, you can see when it's so the spring has a natural length, and so that's the equilibrium position. And if you stretch the string, the string will the spring if you stretch the spring from its equilibrium position, you lengthen it, so make it longer, and it will tend to go to the equilibrium position. So it will tend to make a tension. And if you compress it, there is a compression, and it will still have the tendency to go back to the equilibrium position. So that's why it is on the opposite direction. And the spring has a Hooke's law and ensures that the acceleration is proportional to the displacement. So another example is a pendulum with a small angle of amplitude. So if you hang a small ball, a small mass from a long string, and you hang it with some fixed point, and you let it do the small oscillation with a small amplitude oscillation. So it just moves back and forth. It can be approximated into a simple harmonic motion. So we aim to describe the simple harmonic motion in this section. So according to the definition, about the acceleration and the displacement, right? So we derive the ordinary differential equation to describe the system. Like the system can be mass spring oscillator, or we just take the mass spring oscillator as an example because this is the best approximation. So you can see pendulum can also do, but pendulum must require a small angle amplitude. This makes some error on the motion. So it is not a good approximation to the SHM. So we take the mass spring oscillator as an example. We can write the equation into this form. So k is that constant we have introduced before, and d squared x over dt squared is the acceleration. So v is dx over dt, and derive it with respect to time again, we get the acceleration d squared x over dt squared. So this thing at kx equal to 0, that is same to the equation 1. Anyone has has a question? You're welcome to ask. No? Okay, maybe I should continue. So this is a second order linear ordinary differential equation with constant coefficients. Like I remember the last time in the second section, I introduced the classification of ODEs. So this is according to the classification. This is second order and linear with constant coefficients. So second order means that is harder than first order, and linear and constant coefficients means that it is somewhat easier than the ODEs that don't have these properties. So we have an experimental rule of this type of ODE. We should note that only this type of ODE has this experimental rule, right? Trying solutions in the form e to the power of lambda t. So t is the independent variable, right? So if your independent variable in the ODE is x, then you should use e to the power of lambda x, right? So here we use t. So this is a good idea to try this. And we must note that the complex values for lambda is allowed here. So lambda can be square root of -1 and or square root of -1 plus 1, like these. So then we substitute this solution, guess the solution into the ordinary differential equation. The first term, d squared x over dt squared. So I think you know how to derive functions. So this solution is a function, right? So if you derive it twice, so you get two lambdas multiplied in the front. So there's lambda squared and e to the power of lambda t plus k times, just substitute the solution inside, right? So because e to the power of lambda t can never be 0, you can observe the e to the power of lambda t function, right? So this curve never touches 0, so we can just cancel them, and we get lambda equals plus or minus square root k times I, where I is the unit of the imaginary number. So so I equals square root of -1. So we define it as that. And so we consider Euler's equation, e to the power of ix equals the cosine of x plus I sine of x. Note that this x is not that x, right? This is just the Euler's equation. So it represents a variable in the Euler's equation. It is not the displacement. So using this equation substituted into the original function, we can explicitly write out two specific solutions. So this is the two specific solutions, x1 and x2. So these two, if you substitute back into the ordinary differential equation, they all satisfy, right? But they are not all the solutions. How do we get all the solutions according to these two? So we have important property of linear ODEs. So when linear ODEs with right-hand side 0, so in this case, so the right-hand side is 0, like the equation 2. So we have the right-hand side 0, and we have this important property. So if f1t, like so f is a general expression of x, right? So we can understand that as x1 and x2. So if x1 and x2 are both specific solutions for a linear ODE, then c1 f1 plus c1 x1 plus c2 x2 is also a solution. So c1 and c2 are arbitrary constants. So you can choose c1 and c2 like you can arbitrarily choose them, and so c1 and c2 can be chosen independently, right? You choose them arbitrarily and independently, and the solution you get is also a solution for this ODE. So here we give a proof. The general formula of the linear ODE, if you call back to my last session, so it's like in form of this form, and so x is the so the first term p0 of x, p0 times x is the zeroth differentiation term, and there is also other orders differentiation term, and it's written on the right hand side. The other term is a summation of these other terms, and this thing equal to 0 because we said the right hand side is 0. So if according to the given f1 and f2 are both specific solutions, so x can be f1 or x can be f2. So if x equal to f1, the right hand side is still 0, and if x equal to f2, the right hand side is still 0, and we get equation 6. So these two equations both establish because f1 and f2 are solutions, and we add these two in equation 6, and we have this. So the right hand side term is because the linearity of differentiation operator, right? So so you have a property of differentiation that if you differentiate the summation of two functions, it is same as the summation of these two functions differentiate respectively. So no matter what is the order of the differentiation, it is also always true. And so this equation 7 gives the proof that f1 plus f2 is also the general the f1 plus f2 is also the solution, and you can multiply f1 and f2 by different arbitrary constants, and you'll find that this is always true. C1 f1 plus C2 f2 is always the solution. So because the second order ODE always have two arbitrary constants that cannot be simplified into one arbitrary constant. So so in this case, we have C1 and C2, and this cannot be simplified into one arbitrary constant because F1 and F2 are different, right? So so we will talk about this simplification rule later on. So the general solution is like this: C1 times the first solution plus C2 times the second solution. So but we can see that there is I as square root of -1 here in the equation. And because this is a physical question, right? Physical question don't always encounter imaginary number. This is imaginary number don't have any physical meaning, right? So real numbers are more desirable in this case. So we can adjust the two arbitrary constants to achieve this. We let C1 plus C2 equals A of A times cosine of phi, and I times C1 minus C2 equals A sine of phi. This can be achieved by solving the C1 to C2. So then then the solution becomes like this, right? So according to the trigonometric identity, well, actually here I got something wrong here. It is the right hand side is A cosine square root of t minus phi, right? But because phi is an arbitrary constant, because C1 and C2 are both arbitrary, so you can just make phi to be negative phi, and this thing is true. So then so we just what do we do here? Actually, we just transfer the two arbitrary constants into other two arbitrary constants. Originally, we have C1 and C2, right? But these arbitrary constants are not good because they give complex and imaginary solutions, and we don't want that. And then we transfer the solution and get another two arbitrary constant, A and phi. So then we found that are real, and so here A and phi, these are not only arbitrary constant, they have actual physics meaning here. A is the amplitude of the oscillation, right? So this represents the maximum displacement from the equilibrium position. And the parameter phi is the phase angle. So this can be determined. These two, A and phi, can be determined when initial conditions are provided. For example, I don't just provide that the acceleration is proportional to and in the opposite direction of the displacement. I also provide initially at t equal to 0. For example, the object is released from rest at one amplitude, and that will be the amplitude and the oscillation. So the initial condition can determine A and phi, right? So so in this case, if a release from zero, release from zero velocity, release from rest, phi will be 0, and A will be that displacement from the equilibrium position, right? So these can be determined when initial conditions provided. This is also a concept from the last section, and so you can see the solution is A times cosine of something. So, and this cosine of something, the thing inside the bracket is varying linearly with time. So cosine of this thing is varying oscillation. Is like oscillation with time. So when time goes by, this x displacement oscillates with when time goes by. So it oscillates with the amplitude A, right? So the physical meaning of the parameters. So the oscillation. When we talk about oscillation, there's other sets of physical parameters. So there's a period t. So period of t is given by 2 pi divided by square root of k. So actually k square root of k is the multiplier of t in front of t, right? So we can easily determine when the thing inside the bracket of cosine increases by 2 pi. So then it completes one complete oscillation, right? Then the time goes by the period t. So the time period is given by 2 pi over square root of k. And the frequency, which is the reciprocal of the period, is given by this square root of k over 2 pi. So these parameters help us to describe and analyze the physical meaning of this oscillator. So the period and frequency. So we must by the initial condition. So the initial condition only affected the amplitude and the phase angle, but the phase angle is just constant. They cannot affect the period, right? So the period and the frequency, they are only affected by the spring constant, which is mk, or the mass m, right? So actually it is just affected by k, but k don't have a physical meaning, right? So we can say the quantity that have physical meaning is mk. Mk is the spring constant, and the mass m has physical meaning, the object mass attached to the spring. So we can adjust mk and m to adjust the frequency and time, but we cannot adjust the frequency and time by shifting the initial condition. And about the mechanical energy of the system, you can analyze this after class according to the equation. So the mechanical energy must be conserved, right? Because we don't introduce non-conservative forces like friction or other tension of the string or something that that transfers the mechanical energy into other forms of energy. So you may analyze the mechanical energy of the system after class. I put a proof that the mechanical energy is constant at the end of the PowerPoint in the appendix part. You can look at these if you're interested. Then we come to the damped oscillation part. This is another. This oscillation are divided into 3 types. We will introduce them one by one. So there's a general derivation of the equation of the system. So in real world systems, actually, damping often exists. So you don't just have the acceleration proportional to the displacement, right? When you move in the air gives you a drag, and when you move in the water also gives a drag. When you try to push a thing that is on the table gives a friction, right? So these are dampings. The damping forces are non-conservative forces. This made the mechanical energy of the system decrease from time to time, and when it decreases, the amplitude decreases, and we will see this phenomenon. So this is a resistive force, and we need a model because a friction is different from the drag of air. Friction of the table is different from the drag of air and water. So a common model for the damping acceleration is proportional to the velocity of the oscillator. And so we can see that the acceleration of the drag, acceleration due to the drag, is proportional to and on the opposite direction of the velocity v. So it must be on the opposite direction of v, because it is common sense, right? Because the friction are always on the opposite direction of where you pushed it. B is the damping coefficient. We call B the damping coefficient, and so we consider the mass spring damper system. The equation becomes like this, right? So this is force analysis. The first term is the inertial force, ma, which is representing the inertia, and the second term is the damping, and the third term is the force exerted by the spring, right? And it must equal to 0. So this can be rewritten. M is cancelled, and so this is our differential equation 14. And we again, because last time we tried e to the power of lambda t, we found that this is a good idea to try this general solution for this type of equation. And then we this time, so we also try substitute it into equation 14, and we get this. So actually, there's also e to the power of lambda t multiplied to this equation, but e to the power of lambda t, as mentioned before, it cannot get to 0, right? So we just cancel it on both sides. So we have lambda squared plus b lambda plus k equal to 0. This is a quadratic function. The quadratic function has equations that we can solve. So lambda equals, this is the general formula of the quadratic equation. And of course, under the square root b squared minus 4k, this can be positive, 0, or negative. So once you want to solve a quadratic equation, you must consider three cases, right? When the solution is there's two solutions that are different, two real solutions that are different, only one real solution, and there is no real solutions. So these three cases corresponds to the three damped oscillations. So the discriminant b squared minus 4k, we have different types of damped oscillations. Okay, so actually I forgot to ask for your questions when the first section ends. Now you may ask questions. Do you have any questions? You're welcome to ask now. Anybody has questions? Okay, so maybe there's no questions. I will continue to introduce the three cases one by one. So underdamped, the title was underdamped. So when we say something's under, in common sense, we're saying something is not sufficient, not sufficient. Underdamped, so the damping is not sufficient. So the damping is proportional to the so the damping coefficient is b, right? So we are saying b is not sufficient. So of course b squared is smaller than 4k, and this thing is negative. So the case one, underdamped oscillation. This is when b squared is smaller than 4k, and the whole thing under the square root is negative. So the roots are complex. There's no real solutions, and the solution is of the form like this. So there's two complex roots, and they are complex conjugates. So they have their real parts. They have their real parts equal, and their imaginary part being negative to each other. So we define that the imaginary part's absolute value is lambda imaginary, and the real part has absolute value lambda real. So not the absolute value of the real part. The real part is lambda real, right? So this thing we can extract e to the power of lambda real t outside, because the real part of lambda 1 and lambda 2 are equal because they are complex conjugate. And so in the bracket, there's arbitrary constants. We had met the factor within the bracket before. So if you remember the simple harmonic motion before, it is c1 e to the power of I something plus c2 e to the power of negative I something. So this something is equal, and the arbitrary constant are in the right place. So it is same in the bracket. It is a simple harmonic motion equation. So as we dealt with, so what we do to the simple harmonic motion. So we write it out, and we try to adjust C1, C2, and make them as A and phi, so that we can get real solutions. We do the same thing, exactly same thing to the thing inside the bracket, and so we get this thing. A to the power of A times e to the power of negative b half t times cosine of this thing. So originally there is square root of k in front of t, right? Now it is just lambda imaginary. So lambda imaginary is square root of k minus b squared over 4, and so this thing is the so we will discuss what is the meaning of this thing later. So let's see first what is the amplitude of this oscillation, because now the oscillation not only contains the cosine and the amplitude, it also contains e to the power of negative b half t, right? So let's see what it will do to this oscillation. So now we can see there's still an amplitude. This is still an oscillation because there's a cosine, right? A cosine always get to 0 and get to the maximum, and get to 0, get to the minimum, and just like oscillating like that. But the amplitude is decaying. The amplitude is not simply A, right? Now, in this case, the amplitude is A times e to the power of minus b half t. So it decays exponentially because the factor before t on the index is negative b half. And this thing is negative, which means that this thing decays exponentially over time. So it is understandable because you have the oscillation, and then you apply a damping, and so the amplitude decreases. So your mechanical energy is transferred into other type of energies. So so the damping effect make the amplitudes be decreased. And because you have the damping effect, the resistive force tends to resist the motion of the oscillator. So actually, the oscillator goes in a smaller speed. So you can observe that the frequency is decreased. So it fits our common sense. The frequency becomes square root of k. So the frequency, as mentioned before, is the thing behind before the t in the cosine bracket, and this thing divided by 2 pi is the frequency, right? So now so originally it is k square root of k. So now it is square root of k minus b squared over 4. And b squared over 4 is definitely positive. So this thing is decreased. And the frequency is decreased. And time period, of course, is increased. So I draw a diagram here. This is an example of the oscillation. So you can see at the time equal to 0, it has amplitude 10. And then you can see you can draw a line in your mind that connects all the maximums of the cosines, and you found that this connects into a exponential curve, which represents the exponential decrease of the amplitude. And although it's decreased due to the damping effect, but it can still pass the equilibrium point infinity many times, right? So as an example, you can imagine there is a pendulum. The pendulum is deflected by you in a small angle, and then it starts oscillating. But because it travels across the air, it is damped, right? But the air is not sticky. The air is not sticky, so the damping is not that heavy. So you can see that the oscillator, the pendulum, passes the equilibrium point, the downward vertical, many times, but before it stops. So you can see this in this curve. The curve passes the t-axis many times before it stops. So in this case, the underdamped oscillation can pass the equilibrium point many times, actually infinity times if possible. But in other cases, like critically damped or overdamped, it cannot do this. Let's see why. So in the critically damped case, we can see critical. Critical, what does mean critical? It means the boundary condition between two cases. The cases can contain lots of cases. It contains a lot of examples, but the critical damped only contain one example, that b squared equal to 4k. So the equal sign is strict, right? So the roots are equal, and the solution is like this. So the equal roots gives one lambda. One solution, we will call it lambda, right? So the solution is C1 plus C2 times e to the power of lambda t. Here we must note that C1 and C2, they are both arbitrary constants. But if we add them together, it will form another arbitrary constant. No matter we choose C1 plus, no matter what we choose, C1, C2, it will always give another arbitrary constant. It will not give anything special, right? So we can simplify C1 plus C2 into one arbitrary constant. And we suddenly found that this is a second order ordinary differential equation, but it only produces one arbitrary constant. So that is not following the rules. But we always need two arbitrary constants. Remember, we always need two arbitrary constants. So this solution is incomplete. It is not the general solution. It is one solution, but it is not general enough to cover all the solutions. So we need to find another specific solution and add them up. What do we do? So we can assume another solution is in the form of f of t times e to the lambda of t, because in this case, the equation 19 gives one. The simplest solution the equation 19 gives is just C1 plus C2 is 1, right? So it's e to the power of lambda t. So we assume that another solution is in the form of this, that f of t times the first solution. So f of t must vary when time goes by, right? If f of t is just a constant solution, it is just like adding C1 plus C2 plus f. it will make no difference. So we aim to find f of t that is not a constant solution, that is not a constant function. So we substitute this because we assume that this is a solution. So we substitute it into the second order ODE, and we found so expand all the differentiations using the product rule of the differentiation, and we get this thing. This has 6 terms on the left-hand side, but don't be scared. We will cancel them one by one. We can observe the term that contains f. Actually, all the terms contain f, but some contains f in df over dt, and some contains f in d squared f over dt squared. So these are the differentiations of f. Well, now we can observe that the terms that contains f without differentiation. It's the third term, the fifth term, and the sixth term. So these are only contains f, and we extract them out, and we suddenly found that f lambda squared e to lambda t plus b f lambda e squared e to the power of lambda t plus k f e to the power of lambda t. This is just one solution for the ordinary differential equation, because if you cancel all the f, you will find that the first term is the second derivative of e to the power of lambda t, and the second term is the b times the first derivative of e to the power of lambda t, and the third term is k times e to the power of lambda t. And what is lambda t? It is the solution. So we're just substituting the solution into the ordinary differential equation. So it must equal to 0, right? F times this thing also equal to 0. So all the f without differentiation has gone. So the third term, the fifth term, and the sixth term, they are all gone. And so because f without differentiation is gone, so we can assume u as f's differentiation. So the first term, d squared f over dt squared, is just du over dt, right? So you differentiate f twice is equal to first differentiate once and get u, and then differentiate it once and get du over dt. So we can rewrite the equation using u and canceling the third, the fifth, and sixth term, and it becomes this thing. Well, e to the power of lambda t, as mentioned before, it cannot equal to 0. We cancel it. So this thing looks better, but it still contains 3 terms. We don't want that, because actually we want the number of terms be small as possible, so it is easier to solve. Anyone has questions? Okay, maybe not.
Hello.
Okay, sorry. Okay.
I really got confused on this, but can you go like one page before?
Like this?
Yeah. Like assume another solution. Like I really got confused. Like from that point onwards, can you like sort of simplify it even further?
Can you type it in the conversation, because I didn't. I'm a bit stuck, and I'm a bit stuck here. Can you hear me very well? Because I cannot hear you very well. Your voice is a bit stuck.
Hello. Am
Uh,
I a little bit clear?
so what's your question?
Yeah. So basically, like assuming another solution to be ft times e to the power lambda t. Okay, we need like two solutions to like generalize, but why are we doing in this fashion? Like I'm a bit confused there.
Well, this is easier to solve, because we cannot just simply assuming other solution is f of t. We're solving that ordinary differential equation again. We're coming back to the original differential equation. We're doing nothing. So we must assume. So we already know one solution of this ODE. It is different than we do not know any solution. So we must use the solution well. So we assume other solution is related to this solution, f of t times this solution. So is it better? Because we must use the information that we already got one solution, right?
Okay, got it.
Okay. So we assume this and cancel e to the power of lambda t, and we get these three terms. And here we found these three terms. We want the number of terms be small as possible. So we observe that there's a lambda here. What is lambda actually? Uh, Actually, it is the solution of that quadratic function. The single solution of that quadratic function. Actually, it is if you want to calculate is negative b half. So we substitute lambda in negative b half. And then we found that the second term and third term also cancelled. And so we get du over dt just zero. So remember the definition of u is df over dt. So just d squared of f over dt squared is zero. So integrate both sides twice, and we get f equal to c1t plus c2. So it's just uh, any equation that are so f is any equation that is linear. So actually, f already contains two arbitrary constants. We can just assume that because we assume that f is a factor before the solution e to the power of lambda t. So it contains two constants. You can see c1, c2 in equation 24, and so we already got two constants, and f's two constant cannot be simplified into one. So this satisfies our command requirement. So the general solution is f of t times e to the power of lambda t, and we write it, expand it out, we get the general solution x equal to c1 plus c2t in the bracket times e to the power of negative b half t. So you can see suddenly cosine disappears. Well, it is easier to understand why cosine disappear because originally we got complex solutions for uh, above the e, so we get uh, according to Euler's equation, we get these cosine signs. So now we have real solutions. So cosine sign disappears. So in this situation, there is no oscillation. The oscillator returns, so the mass returns to equilibrium position as quickly as possible without oscillating. So actually, C1 plus C2T, the first factor C1 plus C2T is increasing. So it is not quite increasing. It it can be increasing very fastly, but e to the power of negative b half t, it is decaying exponentially. So the first factor might be increasing linearly, but the second term is decreasing exponentially. The exponential speed is much faster, actually much faster than the linear speed. So actually, if you draw the solution out, you can see this is decaying. It might pass the equilibrium position once, but it will not pass it infinity times because the cosine term disappears. And it is the cosine that contributes to all the intersections with the t-axis, right? So now we only have one or zero. Maybe sometimes if you adjust the initial condition, you will get no passing of the no intersection with t-axis. So only pass the equilibrium position at most once. So it is decaying very fast. And so it's critically damped. If we want some oscillator, so in engineering, sometimes we want the oscillator to decay as fast as possible because, for example, we are measuring something, and the measuring thing is oscillating. So actually, we cannot observe this as a good good phenomenon because the oscillation makes the oscillation of the reading of a scale, for example, if it's oscillating, we cannot determine what is the real mass of a thing. So we add some damping on this on the scale, and if we add underdamped, we add damping, so the oscillation is underdamped. Actually, it still oscillates, but it decays slowly, rather slowly. But in this case, if we add the damping that is critically damped, uh, the reading of the scale get back to its real value as soon as possible. So it is desirable to add critically damping on the systems on our system. The next section is overdamped. This is another case b squared is greater than 4k, right? So the only last case, the roots in this case real and distinct, and the solution is in this form. You cannot simplify C1, C2 into one arbitrary constant in this case also. So this is the general solution, which is good. And so we will analyze this thing because the oscillator returns to the equilibrium position without oscillating. So this cosine does not exist either, and the return process is slower compared to the critically damped case, because when t is large, the thing with the exponential that is greater is dominant, right? So the exponential is decreasing faster, so it decays faster to zero, and it's just not important compared to the other term. The other term b half plus the square root times t because it so negative b half plus something is greater than negative b half minus something. So the index is decreasing not that fast. So when t is large, this term dominates the solution, dominates the another solution, dominates another term. So it decreases slower than negative b half t in critical damping because it adds the square root of this thing. So I draw the same diagram. This can also achieve passing the equilibrium position once or zero times. So uh, so actually, this curve tends to zero much slower than the case in critically damping. So you can imagine that actually, if I have a pendulum, pendulum is easier to imagine. If I put it in water, it will not oscillate. It will just go back to zero and just stop there, right? But if I put it in some sticky thing like honey, if I put the pendulum in honey, uh, it will it will be staying there for a very long time, and it will start to fall. But when it starts to fall, it will experience a large resistive force, so it cannot move very fast. So, but we want the what we want the pendulum sometimes uh, to go back to the equilibrium point fast, so we can read the actual value of something. But if it's overdamped, sometimes it cannot get very fast. So the time that it gets to the equilibrium position gets very long. So actually, critically damped is more desirable than overdamped in engineering sometimes. So these are the damping oscillations. It always happen in real life. And the third time we are going to discuss the forced oscillation in the last section. So when an alternating external force acts on an oscillator without damping, we have forced oscillation. So this is a definition. Not the so the right hand side is no longer zero. If you remember, the last time in and simple harmonic motion, we have the right hand side of the ODE zero, and this time we have a force on the right hand side. So the system is not passive; it is forced, right? Uh, so the first two sections are passive oscillation. So the alternating external force. So actually, the external force can be applied in any function, right? So f of t can be not only cosine, can be exponential, can be constant, can be even quadratic, or it can be many things. But uh, if it is in oscillation, so the alternating external force, uh, it is the most interesting, and we will discuss this in today. Uh, ma0 is the amplitude of the external force. So m is the mass of the mass spring system, and a0 is the maximum acceleration due to the external force, and omega e divided by 2 pi is the frequency of the external force. So actually the term the factor before t divided by 2 pi is always the frequency, right, of something that it represents. So omega e divided by 2 pi is the frequency of the external force. We write e uh, on the sub-index for external, right? For a mass spring system, so the equation uh, becomes like this, right? Negative kx is the spring's force, and spring's acceleration, the acceleration due to the spring, and the second term is the external force caused oscillation, caused acceleration. So we can rewrite this 27 into we will shift the terms and found make all the terms have a sign plus. So this is also an ordinary differential equation. It doesn't have it have the right hand side not zero, non-zero, and the right hand side is uh, so it is not the right hand side is not only not zero, but it is also oscillating with respect to time. So this time we cannot just guess the solution. We will use our common sense. The common sense is that the resulting will be an oscillating function. So uh, when you're pushing and pulling a pendulum like a swing, when you are pushing and pulling a swing, the swing will oscillate. That is common sense. So we want the result to be an oscillating function, and when you're pushing and pulling the swing, you found the frequency of the swing is equal to your external force frequency. So we expect the solution, a particular solution, to be the form x equal to a cosine omega e of t. So the a is the amplitude and is to be determined, right? Um, and we substitute this into the ODE 28, and we found the second derivative first, so derive it for twice, and we get actually there is an amplitude on the right hand side. I forgot that. Sorry about that. We can substitute x and its second derivative into equation 28, and we get this. So this time, actually, I substitute it into this, and I extract amplitude and cosine out. And in the bracket, there's k minus omega e squared. K minus omega e squared. So actually, we want to solve of a, right? Because the a is unknown. Other terms we know that. So we want to solve a, and we cancel cosine in both sides, and we get a equal to a0 divided by k minus omega e squared. So here we must notice that it is dangerous, somewhat dangerous, to have two things minus each other on the denominator, because there's a possibility that the denominator goes to zero, right? Because when k equal to omega e squared, it is very dangerous to make the denominator be zero. So we must explain this. We better explain this when why do the denominator become zero? Because a will be infinity, right? But we will worry about that later. Now we will see a property. The another property of the ODE that so how do we solve the ODE, the linear ODE with right hand side non-zero? So the general solution of this, we aim to solve for the general solution. We must notice that the equation 29 is just a particular solution. We aim to find the general solution because there is no arbitrary constant in 29. And so what is the general solution? The general solution is decomposed into two parts. The first part is the particular solution that we found before, that is x equal to a times cosine omega et, and a is expressed in equation 31. So, and the another part is the general solution when the right hand side is zero. So we must find the general solution. The general solution is also easy. We can see the equation we met before. If the right hand side is zero, then it turns into a simple harmonic motion. We have met that before. And the general solution plus the general solution when the right hand side is zero plus the particular solution is the general solution when the right hand side is non-zero. So yes, here we give a proof. The general formula for linear ODE is that the right-hand side is f of x. So here we must notice that I got something wrong because the independent variable is t here. I didn't manage to change that, but do understand that because the typing is I just copied it from the last time. So assume the general solution part, as mentioned before, the the thin red part on the property 2 block, the general solution when the right hand side is zero. So we assume that it's f bar. So it consists of t, c1, c2 because the general solution always gets two arbitrary constants. And the particular solution part, the bold black word in property 2, particular solution of the ODE is f star t, and the sum of them will satisfy this. So we add them, and we found that there's four terms on the right hand side. On the left hand side, the first two terms is f bar. It's related to f bar. So because f bar is the general solution when the right hand side is zero, and this thing gives right hand side because this thing is actually the left hand side of that when the right hand side is zero. So the first two terms is actually zero. And let's observe the third and fourth term. The last two terms is the solution that is one particular solution of the OGE. So although it's particular, it is also a solution. So the last two terms gives f of x. So actually, these four terms together gives 0 plus f of x equals f of x. So this thing, we prove that the solution is f bar plus f star is the general solution of the ODE with the right hand side non-zero, right? So the general solution is like this. So we substitute a and phi with c1, c2. So you can see that it's arbitrary constants. And the first term is the original f bar, and the second term is the f star. And these we must note that now we must explain when the denominator becomes zero, we will observe something very special, that the amplitude becomes infinity. So if the right hand side becomes amplitude infinity, the right hand side, the right term dominates, right? The right term dominates the left. So the overall amplitude is also infinity. So The frequency of the external force omega e, not omega e x, that is a typo. Um, so when this frequency of external force approaches the natural frequency, omega zero equals square root of k of the oscillator, the amplitude of the particular solution becomes very large. Uh, so the phenomenon is called resonance. So actually, in real world, we always have damping. So we doesn't consider damping here in this analysis. But if there is damping, there you can observe that the amplitude also gets very large, but it don't get to infinity. And this phenomenon is called resonance. So at resonance, the energy transfer from the external force to oscillator is maximized. So when you push a swing, also a swing, when the swing goes far away from you, you just also when the swing is approaching you, you pull it, and when the swing is going another direction, you push it, and then you will always be doing positive work to the system, and the system will have more and more energy. Because the system has more and more energy, it will increase its amplitude larger and larger, and finally, if you can maintain your force, because you are dissipating the energy quicker and quicker with larger power. If you can maintain the force, it will have its amplitude larger and larger, and it finally becomes infinity if there's no damping. So this is called resonance. The resonance has many applications. So there's a microwave, and the inside the food, the particles are oscillating in this natural frequency, and so the microwave gives a so the microwave oven gives the microwave to the particle in the food, and the microwave is an external force, and the particle has its natural frequency. And if these two coincide, this will largely increase the amplitude of this particle. When this particle has this amplitude increase, it will be hot because that's the definition of heat, right? The kinetic energy of the particles. So when this get hotter, and you will have your food overall has larger heat, larger temperature. That's the working. That's how the microwave oven that works. So it has lots of applications. So yes, thank you for listening. And after this, I have the discussion of energy in simple harmonic motion. I will send the PowerPoint into the group chat. If you're interested in, you can see this. Thank you. Thank you for listening.